Hi, everybody. This is my hand. Hi, I'm waving hi. Um, you have to wave back. If you don't wave back, you're sour. If you do wave back, you're sweet. This is, I would say, the most important theorem in calculus. And normally I would never say a statement like that, the most important of anything, but I think everyone would agree that this is probably the most important theorem in calculus. I just want to give a little historical explanation or a little historical. Um, so you heard of Sir Isaac Newton. He's the guy who invented the figs, I think. Get that was a joke. Fig Newton, get it? And they say that Isaac Newton invented calculus, but what did he invent? I mean, derivatives were around before him, integrals were around before him. Figuring out the breaking things down, figuring out the area under a curve. All that stuff was done. All that stuff was done before Isaac Newton. So what did he like invent? Like everything was there. So he invented what he did is he made a theorem, the fundamental theorem of arithmetic of calculus, which connected derivatives to integrals because derivative calculus or and integral calculus, so there were two separate derivatives and integrals with two separate areas, and he joined them. So basically, Isaac Newton was a matchmaker. And I'm just going to show you, rather than just lay out the formula, which I'll give you the official formula. I think it's easier if I just um, show you how it works. So I'm going to look at a problem here right now. I'm picking a very particular problem. The problem I want to do is I want to figure out the area, which we call the integral from 0 to 8 of x squared dx, which means, of course, the area under the curve y equals x squared um, between 0 and 8. So I want this shaded area right here. Now, here's how Sir Isaac showed how to do it. Again, I'm just going to kind of show you, and then I'm going to put it all in official formula form. So what he did was he showed that all you have to do is take the. See, we learned a definite integral was one thing; it was just the area under a curve. We learned an indefinite integral was an antiderivative, but we never really made any connection between those two things. We just had the same symbol. Well, what good old Sir Isaac said was that take the antiderivative of this function inside here, which is in this case is x squared, and the antiderivative is x squared, x cubed over 3. We don't write the plus c. Plus c is only for an indefinite integral, not for a definite integral. And we evaluate this antiderivative from 0 to 8. And that means we plug in 8 for x. So it's 8 to the third power over 3 minus, now plug in this next number, which happens to be 0, 0 to the third over 3. And this is equal to, drum roll please. Actually, I'm just going to check on my calculator here. 8 to the third. What's 8 to the 8 to the third is 243. Well, let's just figure it out. 64. I'm just crunching my calculator right now. 8. Right. Oh, it's 512. I like that. Now divide the 512 divided by 3, which equals 0.66, whatever. I'll just stick a 7 in there at the end. Now, why is it that I am so so first of all, how? That is the area that is the precise area under the curve. So the precise area under the curve is 513 over 3. Now, the reason I'm so excited about this is because we did the same problem in a previous section in the last section. And we did this as an example of using drawing the little rectangles and stuff. And when we did it in the previous, we drew a bunch of we just broke it up into 8 rectangles, and we got an answer. We got an answer with the rectangles of 170. That was our approximate answer. And to get that approximate answer, if you remember, it was very torturous. We had to draw those rectangles and figure out all the areas and it was a whole mess. I mean, we did it, but it was a whole mess. Whereas this is so simple, super simple. I want to do another one and just show you how super simple this is, and then I'll show you officially what the formula is and how it works. So I just want to find the oh, here we go. So I want to find the integral. I want to find the area under the curve. I want to find the area under the curve from 0 to 2 of negative x squared plus 5 dx. And that, of course, again, to draw a picture of it, that's just it's like an upside down parabola, but we only want this slice from 2. And now let's do this. So first we take the antiderivative. So the antiderivative of negative x squared is negative x cubed over 3. And the antiderivative of 5 is 5x. And we evaluate that between 0 and 2. By the way, these are easy because I have the number 0 there. If we were doing it between between 3 and 7, it would be more work. But what can I say? Sometimes we're lucky. So this is going to equal negative 2 to the third over 3 plus 5 times 2 minus negative 0 to the third over 3 plus 5 times 0. And I wrote this whole thing out, but it's just nothing because it's just 0 times just 0. Anyway, this is going to be equal to negative 8 thirds plus 10, which is what is that? 10 is 2 and 2/3. 7. It's equal to 7 and 1/3. Wait a second. That equals well, let's just make it official. It's 30. That's 22 over 3, which is 7.333. And that's our precise answer, 22 over 3, which is 7.3. It's a repeating decimal. It's 33333 forever. Now, why am I so excited about this? Because if you recall, and you may not recall because you might be repressing the horrible memories, but we did this exact same problem again, drawing all the rectangles and stuff. And when we did that, we got, what did we get? We got approximately 7.3. So we drew 1, 2, 3. We just drew 5 rectangles, and we got an approximate answer of 7.36. That was with a lot more work. And here, this is relatively much less work. We just do we got a much more accurate answer. This is really the precise answer, and pow, we did it. So let me show you, first of all, let me just state the formula much more, more officially. And this is the fundamental theorem of calculus. And give me a second, I'm thinking here. So what I'm going to do now, I'm going to switch cameras. Hi, right, I'm right here. I'm here this whole time. I'm going to share my screen. And here we go. This is section 3. This is chapter 3, section 2, fundamental theorem of calculus. And here you go. The integral from a to b of f prime of x. So yesterday, I mean, in the last video, we usually I just refer to this as small f, and this is capital F. But small f is the derivative. So if I have a function which is a derivative of some other function, and I want to find the area under the curve between a and b, I take f without the prime, which is the antiderivative, plug in the top number, plug in the bottom number, and then subtract. And that, my friends, is the story. That is how the professionals do it. I want to actually take a picture of this. I'd like to give you a rough idea of why this theorem is true. So I'm going to go through a pretty rough sketch of the proof. So let's just say we have a curve, y equals f of t. And I'm using f of t. I'm using a different variable because I want to have x to be down here. So Suppose I have a function, I'm going to call this a of x, and a of x is the area under the curve from this point here all the way until x. So this whole area from our starting point all the way to a, I don't know, call it 0, it doesn't matter. So a of x, which means if x becomes bigger, I get a bigger area. If it becomes smaller, I get a smaller area. But right now, this is where we're at. Well, what happens when I change, if I go to a, if I change x a little bit, and this point over here is going to be x plus a little bit more. I'm going to say delta x. Well, what happens to the area? What happens to the area of the curve? So basically, I'm adding on this little strip here. Now, the height of this little strip, the height. So let me just, I'm just going to draw it here. The height of this strip is roughly f of x. You know, it's not exactly f of x. It's not exactly f of x, but it's roughly f of x. So I'm going to say the height is f of x. X being that point right there, and the width of this strip is delta x. Well, how much does the area change when I add this little strip on? What is delta? That's the area under curve from 0. So the change in the area is going to be, the change in the area is just going to be the addition of this strip. And the area of that strip is f of x times delta x. Now, if I make this strip very teensy-weensy thin, then the delta A becomes a dA, because that's what dAs are. That's the whole point of calculus, infinitesimally thin things. And that equals f of x just stays what it is, but the delta x becomes a dx. And now I can bring the dx to the other side, so I get dA dx equals f of x. But wait a second. This means that the derivative of the area is the original function. So what is a of x? If a of x is the area under the curve from a to x, a of x, I've been calling it a of x, but really what I've been calling a of x is really just the integral from 0 to x of f of t dt, and the derivative of this a of x is the original, is this inside function here, is f, which means that if the derivative of a is f, that means that a is the antiderivative of f. And that's the basic reason why this incredible theorem is true. And I'm going to show you a whole bunch of examples right now of how to use this theorem and how amazing it is, because we get the answer, we get a much more precise answer than we were getting before, and we get it super fast. So this is the most, in fact, usually if you're like most of my students, you probably hate me at this point, because why did I make you go through all those horrible rectangles when this is so much easier and better and faster and accurate and this and that. So feel free to so hate away. Anyway, let me do another problem here. Let's get another problem here. I want to find the area. I want to find the integral. I want to find, let's see, the area under the curve. Y equals x cubed plus 1, which looks something like that. And I want to find the area from, I'm going to go from I don't know, 3 to 7. So I want the integral from 3 to 7, see I'm making harder numbers here, of x cubed plus 1 dx, and that's going to equal x to the 4th over 4 plus x, evaluated between 3 and 7, and that's going to equal 7 to the 4th, oh, I'm doing this, 7 to the 4th over 4 plus 7 minus 3 to the 4th over 4 plus 3. And let's see, I'll need a calculator here. 7 to the 4th is, what is 7 to the 4th? 7 to the 4th is, what is 7 to the 4th? 7. Yeah. That this equals 2401 minus 81 all over 4 plus 7 minus 3. Well, that's easy enough. I can do 7 minus 3. 24 for minus 81 equals, right? And then we're going to divide that by 4. Wow. Went in perfectly. Look at that. And this equals 584. Look at that. Look how easy that was. We got the area, POW, simple, straightforward POW. And this is truly a powerful and amazing formula. And this is why, because we get these areas so beautifully and perfectly. Let's do well, let's celebrate by doing another problem. I want to do a lot of problems now to help give you, just give you the idea how to work this stuff, this amazing formula. Let's find the area under the E curve. I want to find the integral from, let's see, 1 to, ready for this? To 2 of e to the x dx. Well, the antiderivative of e to the x, as you know, is just e to the x. I'm going to evaluate that between 1 and 2. So this is just going to equal e squared minus e, which is, let me look at a calculator what that is. E, let's see, 4.67. It's actually an infinite. It actually goes on 4.67077. It goes on forever, but I'm just gonna drop it off at that. And that is amazing. We got a very now again. I could have done this drawing all those little rectangles, and I could have done that, but we don't have to. We don't have to. Let's do one. Let's see. Since this is such a radical theorem, let's do one that has to do with radicals. See what I did there? So I want the integral from. I'm just picking random numbers from, let's say, make it 4 to 9 of the square root of x dx. Okay, so first we want to find the antiderivative, not the derivative, but the antiderivative. The antiderivative, now let's rewrite this in exponent form. So based on the power rule that we did in our previous video, the power rule for antiderivatives, this is going to be x to the 3 halves over 3 halves, which if I just write that a little bit better is x to the 3 halves times 2 over 3, because I just flipped that. And now I'm evaluating this between 4 and 9. So the answer is going to equal 2 times 9 to the 3 halves power over 3 minus 2 times 4 to the 3 halves power over 3. Now, how do you handle this? Well, first of all, when you have a fractional exponent, the bottom number is the root, the top number is the exponent. So first I'm going to take, this means I'm taking, this really is the same thing. Let me rewrite this in a weird, crazy way, just to make it easy to visualize. This is really 2 times the square root of 9 raised to the 3rd power minus 2 times the square root of 4 raised to the 3rd power over, I'll put it all over one fraction. And that equals, something on 2 times, now the square root of 9 is 3. 3 to the 3rd power minus 2 times, I could have factored out that too, but I'm not going to bother anymore at this point. The square root of 4 is 2, so it's 2 to the 3rd power over 3. And that is equal to, I know I'm doing a million steps here. You don't have to, if you could do it in less steps, fine. I just want to step it out, so you see step by step exactly what I did. So this is 2 times 8 minus 2 times 27 over, I'm sorry, what am I doing? It's backwards. 2 times 27 minus 2 times 8 over 3, which is equal to 54, which is equal to 54 minus 16 over 3, and that's 54, 44, 38. Is that right? 54 minus 34 plus 4, 38. And 38 over 3 is, drum roll, it's about 12.6. I think 12.67. So it's 12.667. And there you go. That's our answer. And again, it's really 12.66666666 forever. But just I'm just stopping. So that is it. That is the area under the curve, e to the x, between x equals 1 and x equals 2. And again, an amazing, just an amazing formula, an amazing theorem, and it just makes all these problems, which would have been so much work, drawing all them rectangles. Not that we don't love that, we do. So there we go. The integral from 1 to 2 of e to the x is equal to 12.666. And don't forget, whenever you have it, as I mentioned before, I mentioned this in the previous video, and I probably mentioned a bunch of times more. When we have a definite integral, meaning we have these limits of integration numbers on top and bottom, this thing here is equal to a number. It's not equal to a function. This is not an antiderivative. An antiderivative is a function. But once and that's an indefinite integral. Once I have these numbers on top and bottom. Oh, I'm sorry, I'm looking at the wrong problem. Oh, I was looking at the wrong thing. This is equal to that. Whoops. That's not e to the x. I'm sorry, it's the square root. That's the square root. The e to the x one was 4.67. So this here is a number. It's not a function, it's a number. This is the number of square inches or square meters or whatever the units are, square chihuahuas, under this curve, and there you go. I wonder what'll happen if I get we mentioned yesterday the idea of things being positive and negative and canceling out. I wonder if that's still going to happen. So let's do a nice simple example. I think again, this is an example that we also looked at previously. So in a previous, again, the previous video, we looked at this diagonal line here is y equals 1 minus x. And we said it's very clear to us that this is this triangle, I guess, really has an area of 1/2 because the base is 1, the height is 1. And here also. So that means if I take the total area, you expect that the integral from 0 to 2 of 1 minus x dx, you would expect that to wind up equaling 0 because this positive area is equal to that same negative area. So let's check it out. Let's see if that works. So that's going to equal the integral. This is going to be equal to the antiderivative of 1 is x. The antiderivative of x is x squared over 2. We're evaluating that between 0 and 2, so I'm putting 0 and 2. And that's going to equal, well, just 2 minus 4 over 2, which is equal to 0. It's just 2 minus 2, which is 0. So the integral from 0 to 2 of this function is 0. And that's the quote area. Now, again, it's not the actual area of how much carpet it would take to carpet this, but when we do integrals in calculus, area is directed area or signed area. So that's a positive area, that's a negative area. The two cancel out. But let's look at this. Let's do each little triangle separately to see what we get. If we do let's see this triangle first, the left triangle first, 1 minus x dx. So again, that's going to be the same antiderivative, which is x minus x squared over 2. And that's between 0 and 1. And that's going to equal to 1 minus 1/2, which is equal to 1/2. So this area of this little guy here is 1/2, which is not surprising me. Now let's do the other little triangle. The other little triangle is going to be the integral from 1 to 2. X goes from 1 to 2 of 1 minus x dx, which again, this is all the same. The same antiderivative, that's not changing. 2 minus x squared over 2. But let's see what happens when I do this. This becomes 2 minus 2 squared over 2, which is not what I'm doing here. Oh, I'm sorry. Whoops. So it's 2 minus 2 squared over 2 minus 1 minus 1 squared over 2. That's equal to, this is 2 minus 4. This is equal to 2 minus 4/2 minus 1 minus 1/2. And that becomes, so this is just 2 minus 2. And this is just negative 1/2. I'm sorry, negative positive 1/2, which is equal to finally negative 1/2, which is what we'd expect. So again, the area, so to speak, of this triangle is negative 1/2 because it's under the x-axis, because that's the x-axis, and it is whereas this triangle has a positive area because it's above the axis. That is a negative. Again, physically, if this was a geometry class, I'd say this is absurd. They both have an area of positive 1/2, from a geometry point of view. From the calculus point of view, we're looking at this as the directed area, or the area, under the. Oh, speaking of directed area, we mentioned what happens when you reverse this. So let's look at the one let's look at this first one. It's above, right? So we said if you switch the limits of integration, so I'm gonna take the 1 and put it on the bottom, and the 0 put on top. I'm putting the 1 on the bottom, and the 0 on top. Oh, I'm sorry. The 1. Well, I can't even do this all over again. I'm gonna do the 1 on the bottom, the 0 on top, of 1 minus x dx. So I'm looking at this same triangle, but I'm going in the backwards direction, the opposite direction. So this is going to be, again, this is just going to be x. Notice this part never changes, the antiderivative, from 0 to 1, and that's equal to basically 0 minus 1 minus 1/2, and that's negative 1/2. So if I do the top triangle in the usual direction, in the positive direction, then I get a positive 1/2. If I do the top triangle in the opposite, in the backwards direction, the negative direction, I get a negative 1/2. If I do the bottom triangle in the positive direction, I get a negative 1/2. So again, it could be, all these things are possible. It could be positive, it could be negative, depending on whether it's above the axis, below the axis, positive, negative. All these different things are all possible. So that's I think a very insightful issue. Okay, everybody, I'm going to stop this video now, but I'm going to make another part, for the same section. So, bye-bye for now, but I'm going to make another video very shortly, and I will see you all later. Bye.